Chemistry 2 time, Hayes.
My little family tree is related to that person over there.
Oh, I don't have to write that. Every single time in this class and only this class I write it. Shh. Chemistry 2 time, we're talking about reaction rates.
Are you videoing this?
Yeah.
Oh, you are.
Reaction rates. The whole first part of the video is me trying to talk about why I shouldn't write that on the board, and in the background is you guys just yelling at each other. So that's great. Hazel know that he feels right at home. Hazel will feel right at home. Okay. Reaction rates. Let's real quick define. Well, you know what a chemical reaction is, I hope. How do we know if a chemical reaction has occurred? I'm not talking about the evidence. Not always. No. What is the fundamental thing that must happen? What must be different before and after?
The product.
The products have to be chemically different from the reactants. You know, like if we have water, ice, and that melts, that's not a chemical reaction because it's water before and it's water after. That's not a chemical reaction. But if we have hydrogen peroxide decompose into water and oxygen, well, water and oxygen are different from hydrogen peroxide. That's what a chemical reaction is. What does a rate mean in general? I'll give you some examples of rates. Can you drive a vehicle? Can you drive a Chrysler 200, model year 2015? How fast can you drive it?
Real fast.
How fast do you drive it, commonly?
70.
70? 70 what? 70 what? Miles per hour. Miles per hour is a speed, a velocity, it's a rate. Any unit divided by another unit is a rate. And this is kind of a fast definition. I should say any quantity divided by some other quantity is a rate, but we measure them in units, obviously. For instance, the urinal, I don't know if you guys know about urinals, but on the urinal in the boys' toilet, there's a little sign on it, not a sign, but like the markings on the urinal say 0.8 GPF. GPF stands for gallon per flush. So a unit, gallon, divided by another unit, flush. Well, flush is not really, but and that's a rate. That's telling me how much, what is that rate telling me? The rate of what per what? Gallons per flush. That means that every time I flush it, it's this. Yeah, it's this volume of water that's being used, and that's a rate. So if we're talking about reaction rates, what are we probably talking about? How are we going to measure it? What's our top unit and our bottom unit going to be? There's two ways, two common ways.
Reaction rate. How much substance over the time?
Yeah, so there's going to be time on the bottom, and then amount of substance. I'm going to put amount on top. And when we say amount in chemistry, we almost always mean it's going to be measured in moles. But we end up actually measuring it, because this is kind of difficult, we end up usually measuring it in molarity per unit time, or grams or kilograms per unit time. So it's either molarity per unit time or mass per unit time. And reaction rate questions like this are really pretty simple. For instance, there's an example problem on page 562. I'll just read it. We won't do the math for it, but I'll just read you the kind of thing you can expect to see. In a reaction between butyl chloride and water, the concentration of butyl chloride is 0.220 moles at the beginning of the reaction. At 4 seconds, the concentration of butyl chloride is 0.10 moles. Calculate the average reaction rate over time. So what that means is that you would find the difference in molarity. We could express it this way: delta molarity, delta grams, delta kilograms, delta moles. But it's the change in.
Are you going from your initial to, like, what are you subtracting?
Delta always implies whatever it is, final minus initial. It's always final minus initial. So for instance, if I'm trying to find your change in speed, if I'm calculating your acceleration in your snazzy new Chrysler 200, probably color magenta, I don't know. But, like maroon, like old lady red? Good. Okay. Old lady's blood red. Okay. I would have your final velocity, 70 miles per hour. Your initial velocity was 0. It took, I don't know, maybe 5 seconds. So that would be roughly 14 miles per hour per second. Anyway.
So like this example in our, it wouldn't be negative. No, it wouldn't.
There can be. Well, I don't know if a reaction. Yeah, there can't be a negative reaction rate.
Okay, thank you.
Your book goes on to talk about conceptually collision rate, activated complexes, and activation energy. Effectively, when a reaction occurs, it relies on these things to physically touch they have to be colliding. So that's what the collision theory is that if we have, for instance, hydrochloric acid plus zinc yielding zinc chloride plus or hydrogen gas, in order for these two things to react, there has to be a collision between the hydrogen chloride molecule and the zinc atom. They have to literally collide, and then that smooshes together, and these two things are formed instead. That's the collision theory. That they have to touch in order to...
Molecules have to touch.
Not necessarily molecules, but particles have to touch. Particles have to touch in order to react. And then the best way I can think of, just to briefly describe activated complex and reaction energy, is just this chart on page 565. I'm going to hold it up for the camera, and then you can pause it even if you don't have your book. Have to touch to react. Yeah. Here's the chart. Oh, come here. Come here, chart. Pause it. Hurry. I'm gonna. There we go. Now pause it. Okay. So this chart, and this is the way you can look at it in your. On page 565, it's chart or figure 16.5. 565. The little diagram on 564 talks about the collision theory, but I'm talking about the activation energy. So basically, there's a certain amount of energy that's on the y-axis, and then there's time effectively on the x-axis. We start out with a reactants that have a certain amount of energy, and then there's an activated complex, which is like the part of the collision where they're touching. That's the activated complex. So for a moment, all of these things are bound together, and then they separate into more energy stable compounds, in this case CO2 and NO.
Okay, so this is an activated complex is when what?
Is when the initial particles are temporarily bonded. And that's called, and you know the word complex means kind of like a group of things momentarily working together, like a complicated system, kind of.
Complex is when
There's a,
particles are temporary.
yeah. And when I say initial particles, I mean what part of the chemical reaction? Reactants, yeah. So the reactants are temporarily bonded to form the activated complex, and then that activated complex separates another way the new products. Could this reaction occur if the energy of the products were higher than the energy of the reactants? Look at it.
Say it again?
Could a chemical reaction occur? It wouldn't be this one, but could a chemical reaction occur, looking at this chart, where the products had a higher energy than the reactants?
Yeah.
Yeah? Yeah, it would have to be endothermic, though. It would have to absorb energy from the environment, and really I should say endergonic. It had to absorb energy somehow.
Could the reactants, if the what?
I'll show you. So if, for instance, if we had,
No, I think I understand what you're saying.
I'll just do the graph for this one, then we'll do another one. So here we have energy, and here we have time. So at the beginning I'll have my, I'll have some, no, my reactants, you mean. So I have my hydrogen chloride, and my zinc. They will temporarily bond to form an activated complex, which is not shown here, but this will be the activated complex, which usually has more energy, and then the zinc chloride and hydrogen gas have less energy. And this reduction in energy, remember from chapter 15, this release of energy causes this reaction to be exothermic in this case. It must necessarily be exergonic. Yeah. Oh, this one's exothermic. It's the products have a lower energy than the reactant, so energy must have been.
Higher energy than the reactants.
The products have a lower energy than the reactants.
Look at how high it is.
The reactants are high.
The different ones. Or looking at the different.
Thanks, Sky.
Let me just,
Yeah.
let me bring it back. Give me a
Thanks, Sky.
second,
Yeah,
okay,
so-
bring everyone together.
So some of us, we were both right because I was looking at 16.5.
Because I knew I was right.
And Dali was looking at 16.6. But then I'm going to give you another example. So for instance, if we have,
And we're moving.
if we have water plus carbon dioxide in the presence of sunlight, release glucose sugar and oxygen gas, what is this, first of all? What is this? Photosynthesis. That one would look like there will be these reactants have a lower energy. There's an activated complex here, which is, I'm putting that here. But the final result, and this might be, actually it probably is, it has to be lower than the activated complex. but still higher than those. This release of energy, this absorption of energy has to come from somewhere. And so this amount is, it must necessarily be endergonic. And the reason I picked this one is because this is not endothermic. It doesn't absorb heat energy, but it absorbs sunlight. And so it's the word for absorbing energy in general is endergonic. And the reason and the word for releasing energy in general is exergonic. But this one is also exothermic. So once again, this little thing here is the activated complex. Oh, and sorry, before you ask your question, the difference between the products or reactants and the activated complexes, this amount is important, and it's called the activation energy. So this can't occur without that much energy, and this can't occur without that much energy. And the reason that's important is because if there isn't enough energy in the environment, neither of these reactions can occur, and that relates to spontaneity, which is something we didn't get a chance to touch on in 15, but that it does exist. And so this one, obviously, this doesn't occur when? When does photosynthesis not occur? When there's not sunlight. Obviously, the activated energy just isn't there. And this one, if we have the temperature low enough, not just the temperature, but in one example, if we have the temperature low enough, even if we react hydrochloric acid and zinc together, they won't form this energy to make the activated complex. Another way of thinking about it is their collisions won't be fast enough by collision theory.
So when is there an intermediate?
That's a different thing. The intermediates are they're.
It still has an activation.
Yep.
Energy.
When we start talking about the reaction rates, we'll talk about intermediates in. I don't know if we'll actually even touch on that, but an intermediate is something. If this happens multiple times, so for instance, if we had, let me try to think of an example. If we had sulfur and oxygen combining, and that made sulfur trioxide, and then that sulfur trioxide decomposed into sulfur dioxide, instead of having one little lump of activation energy here, let me see if I can, this will be a real guess, so if you find that this is wrong when you're watching this video, don't at me. So let's say I have sulfur and oxygen here, and they're going to form, this would be a lower energy, they're going to form sulfur trioxide. Obviously this is not a balanced equation. And then that's going to decompose into sulfur dioxide. In this case, there still is activation energy here, but this sulfur trioxide is the intermediate.
Is there activation energy at both of those points where it goes out? You know what I'm saying?
Yeah, and there probably should be. Actually, I don't know if the intermediate might count as the activated complex here. It has an activation energy. You know what? It would actually have to, because otherwise it would just spontaneously do it, which it does. So yeah, there's an activated complex here too. But the intermediate is the sulfur trioxide. And then two of those would have to run into each other and then split into sulfur dioxide to be more energy stable. And the main thing I'm worried about here, and the reason I didn't want to use this example, but I can't think of another one, is that this actually might be lower energy than sulfur trioxide. I don't actually know, so don't take this as the gospel truth. It's just an example of what an intermediate or intermediary. So it's just another, well, listen, the difference is the intermediate is chemically stable. This isn't just these two things crashed together. It is its own compound, but then it decomposes on its own into sulfur dioxide too over time. So that's the difference between an activated complex and intermediate. I'm going to get that off of there before someone puts a comment. Comments are disabled for this video. Okay, that's all just kind of background, and I want you to understand that at a conceptual level, don't be surprised if there's a graph like this and you have to read it, but only conceptually. You know, like it'll say, is this reaction endergonic or exergonic based on this chart? And that shouldn't pose too much of a problem. Endergonic means it absorbs energy. It doesn't have to be endothermic, although usually all endothermic reactions are endergonic, and all exothermic reactions are exergonic, but they're not.
When you touch it, it's cold because it's not letting out
Yeah,
any.
endothermic. And endergonic doesn't necessarily be cold because it might be absorbing some other kind of energy, sound or light or radiation or bing bong or whatever. Yep. Hercules, not a sponsor.
Now
We'll,
it's never watched.
we'll listen to Hercules Disney songs after this, not a sponsor. But we do have to get through this first. Okay,
Are we almost done?
no, we're nowhere near done, and that's why I'm trying to get through this. I'm going to say these. These are in your book, and I'm going to say these out loud so that you know that I know them, and so that you know you're supposed to know them, but we're not going to write them on the board. The things that can change the rate of a reaction are,
Things?
this is in your book too. You already did your outline. Look.
Hang on.
Look. What I'm going to do is read you the subtitles of lesson 2. Okay. We want to do it the hard way. 1, the nature of reactants. It's just the truth that some things react faster than others. The example here is the zinc and copper both in nitric acid. No, sorry, both in silver nitrate. And the zinc is reacting more quickly just because it's zinc and because it's not copper. The other thing that affects other thing that affects reaction rates is the concentration. Higher concentrations mean faster reaction rate. You remember the zinc and hydrochloric acid I just have up here? And that we've done that in the lab and it makes a balloon full of hydrogen. I can make that reaction happen faster if I use more concentrated hydrochloric acid, and I can't really make the zinc more concentrated because it's just zinc. But I can change the next thing, which is surface area. So if I put zinc chunks into the hydrochloric acid, that reacts at a certain rate. But if I put powdered zinc in there, it reacts much faster. Why do I use zinc chunks instead, do you think?
Wait, what did you say?
I'm talking about the reaction we sometimes do where I have a flask of hydrochloric acid, I put some zinc in there and I put a balloon over it and it builds hydrogen up and we blow the balloon up, you know? And what I do is I use concentrated hydrochloric acid to make it happen faster, so the balloon fills up faster. And another thing I said I can do, because that's changing concentration, but another thing I can do is make the zinc have a higher surface area. I can't make the zinc more concentrated because it's just zinc. I can't make it like super zinc. Higher surface area makes it react faster, not because there's more. Even if we have the same mass of a blob of zinc and powdered zinc, the powdered zinc would react faster because it has a higher surface area.
Is that higher concentration?
Yep, higher concentration means reacts faster, and
Higher surface area?
higher surface area, and higher temperature. Yep. But the reason I don't use the powdered zinc for that particular reaction is because it can be too fast, and then it kind of bubbles up, and then the balloon gets hydrochloric acid in it, and then when we pop the balloon,
Okay.
hydrochloric acid gets on my friends.
So you're saying that if you put a chunk of zinc in something, since it has less surface area
Yep.
than the powder.
Yep.
Okay.
It reacts slower because it has less surface
And
area.
the same with temp, right?
The same with temperature. Yep. Higher temperature means faster reaction. Higher temperature means faster reaction. And then you have to know the definition of catalysts and inhibitors. This is from physical science, this is from chemistry, and we're talking about it again. A catalyst does what? Speeds up a reaction, and an inhibitor slows down a reaction. And neither one of them is part of the reaction at all. They're not part of the reaction at all. Like Skylar's lab was catalysts. Do you remember that? So the reaction of hydrogen peroxide just sitting in a little cup, all on its own, this reaction occurs all the time. Just sitting there. This reaction is just always happening. Just pretty slowly. That's why when you buy hydrogen peroxide at the store, it's in a brown bottle. When I buy it pretty concentrated, I buy it in an accordion bottle because the oxygen that's generated will blow up a regular bottle because it's a gas. But this happens all the time, relatively slowly. The light from the sun will make it happen faster, which is why it's in the brown bottle. But also, adding a chemical catalyst like manganese dioxide or yeast or potassium iodide or blood, all those things make this reaction. They don't change the reaction. They just make it go faster. So we could put blood here. We always put a catalyst above the arrow, which means that the blood was used to make it go faster, but I could get the blood out again if I wanted to, or at least all the chemical components. It probably would have ruined the cells, but I could get all the chemical components of the blood out again if I really wanted to. Same thing with the potassium iodide. If I was worried about saving the potassium iodide, I would just let this sit there and dry up, and my potassium iodide would still be potassium iodide. It'd still be literally the exact same thing I put in. All it did was, so basically, in other words, the catalyst and inhibitors don't take part in the reaction, they just make it go slower or faster, respectively. Okay, now we can math. Or I don't know, math is kind of, now that I've written math halfway up on the board, it kind of makes me sad to have written it because it's not really very mathy. What we're going to write rate laws. So we call this rate laws. Rate laws. And the simplest version of this, we just write rate equals K A. Where rate, obviously we know what rate is. Rate is rate of what specifically?
A substance
The rate of what though?
of A, of the reaction.
Of reaction. K is what we call the rate constant, which varies from thing to thing. It's a specific rate constant. You will be given it if you when you do the actual math with it. It's unique for every reaction, and the units are unique too. The rate will be, you'll find this eventually in, we measure the reaction rate in molarity per second, or molars per second, usually, or moles liters per second, or moles per second liter. Anyway, molarity per second. But the rate constant can be, I'll just put here, unit varies. It depends on what the A is, where the A in brackets, and the brackets are super important for this, is the concentration of A. In fact, from now on, this is not the only time this will apply. When you see a substance in brackets, that means the concentration of that substance. And that's going to be measured in moles per liter, or molars. So far, so good. So pretend we were,
M is molarity.
yeah, molarity, or molar, I say. That's the unit is called molar. The quantity is molarity, but the unit is molar. So I would say something like, if I had 0.35 molar hydrochloric acid, that wouldn't work for this one, or let me use one that will work. 0.35 molar hydrogen peroxide, this would be the rate law for it. So rate equals, this would have a specific K that would be given to you, and then you would just put 0.35, and that's all you would do. So that's for what we call first order rate laws. First order. And the order of a rate law explains how the reaction changes depending on. For first order ones, it's a linear function. Which, in other words, in case you're not up on your algebra 2 like I'm not, a linear, or algebra 1 probably even, a linear function means that as the concentration of A increases, so does the rate at the exact same amount. Like if we double the concentration of A, what happens to the rate? It doubles. If we half the concentration of A, it halves. So this is called first order. For other order of reaction, as the concentration of A increases, changes, I should put, so does the rate, in the same way. For other order, or I'll just put other orders. Sometimes, for instance, if we could have an exponential function where if I double the rate of A, then the rate, if I double the concentration of A, then the rate quadruples, and that would be to the second power function. So that would be given as rate equals K, the concentration of A, raised to the second power. So in this case, these are all still true.
What you said before, then.
I will in a second. These things are still true, what they stand for. But now, instead of a linear function, it's an exponential function. Exponential. And they're not always squared, but as the concentration of A changes, the rate changes squared. So if I half the concentration of A, now the rate goes 1/4 as fast. If I double A, the rate is 4 times as fast. Is there a better way to phrase that?
The other way around? It'd be the concentration squared, right? Because you're
Yeah, that's what it is.
concentration.
Yep, we square the concentration, and that changes the rate. But they still, it's still the same relationship.
The rate would be,
So if I double A, we could do the math, but say K is 1, just to make it easy.
okay.
If A starts out as 2, then my rate is 2, for instance. And then if I double, or sorry, it would be 4. But if I double this,
The rate is half of, right.
but then if I double this to make it 4, I've doubled A, but now my rate is 16. It's quadrupled. Right, so as A changes, the rate changes squared. So if I triple A, how does the rate change? Well, it doesn't. I mean, pretend K is still. No, it doesn't. It still doesn't matter. If I triple A, doesn't matter what A started out as, but if I triple it, how does the rate change? No. Nope. That would be a linear one. Nope.
Say it again.
If I triple A, I'm changing A by 3. How does rate change? No. No.
But it changes.
9 times. 9 times. Let's do the math again. So say I still have 2 here to begin with. Still 2.
Yeah.
So still 1 times 2 squared is 4. Okay? But now I've tripled it. So now instead of 2, I have 6. 1 times 6 squared is 36. So that's 9 times what 4 was. This changes by that much squared. If I quadruple it, how does the rate change? How many times faster is the rate? If I quadruple it, that means 4 times. How much does the rate change?
So 4 times 4 is 16.
Yep, 16 times. You got it. It's just you square it. However this changes, the rate changes by that much squared, like I've written.
Oh.
What if I quintuple it? What if I multiply it by 5? How does this change?
25.
Yeah, multiplies by 25.
Okay, so you just do the number by itself.
Yeah, that's what... You know about exponents, I thought, a second ago.
You was confusing me.
Yeah, I thought you were talking about something completely different.
Okay, so but it's 2 over there, homie.
Yeah. So if let's pretend, okay, we'll show the actual math because it shouldn't be this. K is going to be rate equals, for this one, K, the concentration of A squared. My initial one, I'm going to pretend like I start out with a concentration of 2 molar. Okay, and we're going to pretend like K is 1. K is never 1, or usually isn't. I've never seen it be 1 before. We're going to pretend like K is 1 here, which means we can just forget about K pretty much. It still exists, but so now my rate is going to equal 2 squared, which is 4. But now I'm going to triple, we'll say the 2. I'm changing this by 3 times. Now it equals 3, or sorry, I tripled it, 6 squared, which is now 36. So what? I tripled this, and this multiplied by 9. So it changes the same way as this, squared.
Yeah.
Yeah, okay.
Okay, I thought you were talking about your exponent was changing.
No,
That's
no,
never going to happen
no.
because there's going to be a K.
Yeah, there's going to be a K. So it'll be 36 times 0.45172. Yeah, whatever the K is. But well, it's just multiplying. Okay, that's not even where it gets horrible. Sorry. It can depend on multiple things. Look at page 576. The example here is rate. I'm going to leave this because I'm afraid that it needs to be left. The specific one given on the top of 576 is rate. Yep, rate equals. Yes, we are. K in O squared times H. Oops, sorry, that's not supposed to be an E. H2. I'm going to ask you a conceptual question about this one first. We don't know what K is, so don't worry about the math.
What are you doing?
What do you mean, what am I doing?
Is this another law?
No, this is an example.
Oh.
So the A here represented in the concentration of substance A.
Me
No,
too.
no, this is just an example. What order is this for H2?
1.
Yeah, it's we say first order. It's first order for H2, meaning if I leave everything else the same and I double the concentration of H2, if I double the concentration of H2, how does the rate change?
Double.
Yes, it doubles. It's the same.
Oh, good
It's the same. Okay, what order is NO, nitrous oxide? What order is it for that?
Another order.
Okay, specifically,
That's 2 on the outside.
it's second order. So if I double NO, how does the rate change?
Orders down there.
I know, but I'm not going to go right second order, third order, fourth order. I'd be here literally infinity years because of how numbers work. So if I double NO, how does the rate change?
We have to also
Whoosh. times,
Quadruples.
yes, it quadruples because it changes by the square of that. If I triple H2, how does the rate change? H2.
What is 9 with a...
No. I'm tripling H2.
Oh,
If I triple H2, the rate triples. If I triple NO, the rate
It's 9.
9 times.
What's-
Yes, exactly
what's
right.
9 with a...
Can you say it
Non-tuples. Non-tuples, yeah.
Say that again.
Nominal.
What? Say what again? The whole dang lesson?
Yes.
No.
It's that whole little chunk that you said.
Just now. If I triple H2, I'm just going to say, and you're not going to interrupt me. If I triple H2, the rate triples. If I triple, yeah, that's what triple means. If I triple NO, the rate multiplies by 9. Non-tuples. Okay.
Got it.
Okay, good.
Non-tuples.
Listen, here's the thing that gets people tripped up, and every year I say this, and every year someone gets wrecked. The order, the reaction order, I'll put reaction order so you don't get confused. The reaction order, remember that's to what power it is. It's first order, second order, whatever.
Reaction order.
The reaction order does not depend on coefficients in the equation. It does it depend?
Exponent.
Yeah, but it doesn't depend on coefficients. Like you'll have this reaction will have its own like chemical equation. So for instance, in my chemical equation we did for hydrogen peroxide, H2O2 yields
Hang on, wait for it.
H2O plus O2.
Okay, wait just a second. Reaction
Okay.
order
Does
does...
it? Oh, it does not
It doesn't because it does the thing with
on
the...
coefficients in the equation.
No, what does it go with that? Depends on...
I'll tell you what it depends on in a second, but it doesn't depend on this.
Depends on exponent.
But that's not always given, so I'm going to tell you in a second how we find that. But it does not depend on that. So can we move over here now?
Did you just say they're not given?
Not always. We're going to talk about it in a second. Okay, how is there anything ever? I'll remember that question, Deli. The question, just for the record, Hayes, the question was, how is there anything ever? Okay, anyway, over here, we have, remember this equation? This is hydrogen peroxide just decomposing. Okay?
Yep.
Is this balanced?
No.
Let's balance it.
2.
Well, no, where do I have to put it to?
In front of the H2O2 and a 2 in front of the hydrogen water.
Okay, the hydrogen of water. Great, things are going swimmingly today. Okay, so is this balanced now?
Yes.
Okay, now remember the reaction rate over here, rate equals, and this is true, the reaction, the
I
rate
don't know
here,
which one A is.
it's just, this whole thing would be given. Maybe not
Okay.
balanced, but the whole thing would be given.
So you just guessed it.
The rate of this reaction only depends on what? The concentration of hydrogen. It does not depend, and it's not second order just because there's a coefficient here, which is something people run into a lot. A lot of people, when they start to do this, not you because you're going to do it right, think that this becomes the exponent in the rate law. It does not. Okay, now we ran out of time because you got, it's good for you to ask questions, but we did run out of time. But how we find what order it is, look at the chart real quick on page 576. You'll be given something like the chart on the bottom of page 576. And then you have to compare. So what happened between trial 1, look. We are never going to do this again. Look at the, Hayes is trying to pay attention. Look at trial 1 compared to trial 2. What happened to the initial concentration of A? It doubled. Now what happened to the rate? Go over to the last column. What happened to the rate? It doubled too. So what order is the concentration of A? It's first order. So you use data like this. We will. We use data like this.
3, it didn't change. But
Oh.
then it quadrupled.
Well, no. From 2 to 3, the concentration of A didn't change, but the concentration of B changed.
Oh.
What happened to the concentration? Shh.
Concentration of B didn't change the
But it
first time either.
quadrupled,
Well, we,
so it's a second order.
but Sky, we can't change the two variables at once. So from 2 to 3, B doubled, right? Right? Does it? B doubled. What happened to the rate?
It's quadrupled.
So it's,
So...
what order is it for B?
I told you that.
Okay, so we would write it as this. Rate equals
K.
K, concentration of A. We don't know. And then this is B squared.
Oh.
That looks like I wrote BJ. I didn't write BJ. Bye.